Welcome, science fans, to the fascinating world of chemistry. Chemistry isn't just bubbling beakers in a lab, it's the science of all matter everywhere. From the air you breathe to the phone in your hand, chemistry explains it all. It's why cookies bake, why soap cleans, and why fireworks light up the sky. Every day, you witness chemistry water you drink, H2O, toast browning, the Maillard reaction, and your phone's battery powering up. Chemistry is the ultimate how-to guide for matter, revealing the hidden science in everyday life. When you see the world through chemistry, even a rusty bike or a cup of tea becomes a science story. So get ready. Let's explore the tiny particles that build everything and the rules that make our world work. Welcome to the amazing world of stuff. Let's break it down to the basics, the very foundation of everything around us. We're going to explore the fundamental building blocks that make up all matter in the universe. Atoms, the universe's building blocks. They are the smallest unit of an element that retains the chemical properties of that element. Think of them as the Legos of the cosmos. Atoms are incredibly tiny with a nucleus at their center. This nucleus is made up of protons and neutrons, which contribute to the atom's mass. And then, there are electrons whizzing around the nucleus in specific orbits or shells. These electrons are negatively charged and are crucial for chemical bonding. The number of protons defines the element. It's like the element's unique ID. This number is also known as the atomic number. Change the protons, change the element. Adding or subtracting just one proton transforms the entire atom into a different element with different properties. Elements are pure substances, meaning they consist of only one type of atom. Think of elements like gold, which is made up of only gold atoms, or oxygen, which is made up of only oxygen atoms. These elements cannot be broken down into simpler substances by chemical means. Each element has a unique number of protons, setting it apart from all others. This is what gives each element its distinct characteristics and behavior. When atoms bond, they form molecules, the next level of complexity. Molecules are two or more atoms joined together through chemical bonds. These bonds are the glue that holds the atoms together. Molecules can be made of the same element, bonding with themselves, like O2, where two oxygen atoms bond together to form a stable oxygen molecule. Or they can be made of different ones, creating a vast array of possibilities, like H2O, where two hydrogen atoms bond with one oxygen atom to form water. Compounds are molecules with different elements in fixed ratios, meaning the number of each type of atom is always the same in that compound. For example, water is always two hydrogens and one oxygen. Any deviation from this ratio would result in a different substance. Think of atoms as letters, the fundamental units of language. Elements are like collections of the same letter repeated over and over, and molecules as words formed by combining different letters, atoms, in specific ways. The way atoms bond and arrange determines a substance's properties. The arrangement dictates everything from color to reactivity. That's why H2O is drinkable. It has the right arrangement of atoms for our bodies to process. But H2O2, hydrogen peroxide, is not. Even though it's just one extra oxygen atom, it drastically changes the properties. Chemistry is all about these combinations, the way atoms and molecules interact and transform, and the amazing variety they create. From the simplest molecules to the most complex, the possibilities are endless. It's the ultimate mix and match game of the universe, constantly creating new substances and driving the processes that shape our world. Matter is always changing. It's in a constant state of flux, whether we realize it or not. These changes can be subtle or dramatic, but they're happening all around us, all the time. From the smallest atom to the largest star, everything is subject to change. Sometimes these changes are just in appearance, a superficial alteration that doesn't affect the underlying substance. Other times, the change goes much deeper, resulting in a complete transformation of identity. Physical changes are like new outfits, a different look but the same person underneath. They alter the form or state of a substance, but not its chemical composition. Take ice melting, paper tearing, a simple mechanical process, or salt dissolving in water. The salt crystals disappear, but the salt is still there, just dispersed throughout the water. The substance stays the same. It's still water, and it's still salt, just in a different arrangement. No new substances form, just a change in form or state. The molecules are simply rearranging themselves. Chemical changes, though, are total makeovers. They're not just about appearances, they're about fundamentally altering the nature of the substance. Atoms break and form new bonds, creating entirely new substances with different properties. It's like taking apart a Lego set and building something completely different with the same pieces. Burning wood, a classic example of a chemical change. Baking a cake, a delicious transformation, or rusting iron. These are chemical changes. The original substances are gone, replaced by something new. You can spot chemical changes by color shifts, a visual cue that something fundamental has changed, gas bubbles, indicating the release of a new gaseous substance, or heat and light energy being released as bonds are broken and formed. Baking a cake? It's a perfect example of how heat can drive chemical changes. Heat makes baking soda release gas, creating bubbles that give the cake its light and airy texture. Eggs and flour transform, undergoing complex chemical reactions that change their structure and properties, and you get something deliciously new. The end result is far more than the sum of its parts. Chemical changes are everywhere, shaping the world around us in countless ways. From your kitchen to a campfire, chemical reactions are constantly at work, transforming matter and energy. The key, understanding the difference between these two types of change, is fundamental to understanding chemistry. Physical changes rearrange, chemical changes transform. One is a superficial alteration, the other a fundamental shift. Chemistry lets us understand and control these changes, allowing us to manipulate matter at the molecular level. That's how we invent new materials, with properties tailored to specific needs, medicines that heal and improve our lives, and more. The possibilities are endless when we understand the power of chemical change. Every change tells a story about atoms and molecules, their interactions, and the forces that govern them. And you're the detective, ready to uncover the secrets of matter and its amazing transformations. The periodic table is chemistry's ultimate map. Created by Dmitri Mendeleev, it organizes elements by atomic number, protons in the nucleus. Each box shows an element's symbol, atomic number, and mass. Elements are arranged in rows, periods, and columns, groups with similar properties. Group 1, alkali metals, super reactive. Group 18, noble gases, super stable. The table reveals trends. Atoms get bigger down a group, smaller across a period. By knowing an element's spot, you can predict its behavior, reactivity, and more. It's not just a list, it's a powerful tool for understanding matter. The periodic table is your chemistry cheat sheet. Chemical reactions are the heart of chemistry. Atoms rearrange, bonds break and form, and new substances appear. Reactants go in, products come out, and the properties change. Example: iron and oxygen react to form rust, totally different from shiny iron. Reactions happen because atoms seek stability, often by filling their outer electron shells. Sodium and chlorine combine to make table salt, stable and tasty. Some reactions are fast, explosions, others slow, rusting. Reaction speed depends on temperature and concentration, and catalysts, like enzymes in your body, speed up reactions without being used up. Chemistry is about controlling these reactions to make new materials, medicines, and more. Every reaction is a story of transformation, and you can learn to write it. Acids and bases are fundamental concepts in chemistry, and they're not confined to just laboratories or textbooks. They're actually everywhere around us, playing crucial roles in countless aspects of our daily lives. From the tangy zest of lemons in your kitchen to the cleansing lather of soap in your bathroom, acids and bases are at work. They're even in the cleaning products you use to keep your home sparkling. So, what exactly makes something an acid or a base? At the molecular level, acids are substances that, when dissolved in water, produce hydrogen ions, often denoted as H+. These ions are what give acids their characteristic properties. One of the most recognizable traits of acids is their sour taste. Think about the sharp, puckering sensation you get from lemon juice, or the distinct tang of vinegar. These are classic examples of acidic flavors. On the other hand, bases are substances that produce hydroxide ions, represented as OHE, when dissolved in water. Unlike acids, bases typically feel slippery to the touch and often have a bitter taste. A common household example is baking soda, also known as sodium bicarbonate. To quantify the acidity or basicity of a substance, we use the pH scale. This scale provides a numerical measure of the concentration of hydrogen ions in a solution. On the pH scale, values ranging from 0 to 6 indicate acidic conditions. The lower the number, the stronger the acid. A pH of 7 is considered neutral, representing a balance between acidity and basicity, like in pure water. And values from 8 to 14 signify basic conditions, with higher numbers indicating stronger bases. For instance, Lemon juice typically has a pH of around 2, making it quite acidic. In contrast, bleach has a pH of approximately 13, placing it firmly in the basic range. Now, what happens when you combine an acid and a base? The result is a neutralization reaction where the acid and base react with each other. This process typically produces water and a salt as byproducts. A classic example is the reaction between hydrochloric acid, HCl, and sodium hydroxide, NaOH. This combination yields water, H2O, and table salt, also known as sodium chloride, NaCl. The importance of acids and bases extends to our own bodies. For example, your stomach utilizes hydrochloric acid to break down and digest the food you eat. And when you experience heartburn or indigestion due to excess stomach acid, antacids, which are bases, can help neutralize that acid and provide relief. pH plays a crucial role in the effectiveness of cleaning products. It also influences various aspects of cooking, from baking to brewing. pH is a critical factor in maintaining the delicate balance of your body's internal chemistry, including the pH of your blood. By understanding the principles of pH, you can gain a deeper appreciation for the chemical reactions that shape the world around you. The pH scale may seem simple, but it unlocks a world of understanding about the powerful effects of acids and bases. So remember, chemistry is not just in the lab, it's in every single drop. In chemistry, matter can't be created or destroyed, just rearranged. The law of conservation of mass means the mass of reactants equals the mass of products in any reaction. Chemical equations show this balance. Reactants on the left, products on the right. To obey the law, equations must be balanced. Same number of each atom on both sides. Example, 2H2 plus O2, 2H2O, 4 hydrogens and 2 oxygens on both sides. Balancing equations is like solving a puzzle. Every atom counts. This rule is crucial for making medicines, fuels, and more. It's the foundation of all chemical calculations. Chemistry is precise. Nothing is lost, just transformed. The universe recycles everything. That's the magic of mass conservation. Chemistry is everywhere in your gadgets, kitchen clothes, and even your body. Your phone screen uses special molecules. Its chip is pure silicon, and the battery is a chemical powerhouse. Cooking is chemistry. Heating eggs denatures proteins, turning them solid. Cleaning products use surfactants, molecules that grab grease and wash it away. Clothes made of polyester or nylon are polymers, long chains of repeating units. Plastics are polymers too, designed for strength and flexibility. Chemists are inventing new, eco-friendly materials to fight pollution. Your body is a chemical factory. Enzymes digest food, lactic acid builds up in muscles, and neurotransmitters send signals. Every breath, bite, and thought is chemistry in action. The world around you and inside you is built on chemical reactions. Chemistry shapes your life. Every day, you are living, breathing chemistry. We've explored atoms, reactions, the periodic table, and the chemistry of life. Chemistry explains the how and why behind everything from rising bread to glowing screens. Understanding chemistry gives you the tools to see and shape the world. Chemists solve big problems, new medicines, cleaner energy, and protecting our planet. By learning chemistry, you join a tradition of discovery and innovation. Stay curious, ask questions, explore, and experiment. Whether you're a scientist, artist, or chef, chemistry gives you a powerful perspective. The adventure of chemistry is just beginning. Go explore the world of stuff.